Hi, everyone. So this is my first time at the Polar Data Forum, so I'm really excited to be here. So I'm Caroline Chin from Earth Sciences New Zealand, and I'm an image analyst, so I do a lot of annotating of images. So for almost 2 decades, we've used imagery to understand how seafloor communities live and change over space and time. And so by bringing all this data together in the cloud, including ROSI imagery, we can then use machine learning to uncover patterns and insights or at much larger scales. But before we talk about that, how do we collect this data? So at Earth Sciences, we have a towed camera system called the Deep Towed Imaging System, but we call it DTIS for short. And this towed camera system is rated to go down to 6,000 meters. And we've been using this since 2006, so almost 20 years as well. And it has 2 top-down cameras. So the first camera that I'll show you is our stills camera. So it captures images every 10 to 15 seconds. And this is just an example of what we caught. We took a photo of in 2008 in the Scott Island at about 300 meters deep. And then we also have video. So here's just an example of ice fish nests at Cape Wheatstone at around 100 meters depth, and that was captured in 2023. And generally, we record about 1 hour of transect each time. And we're doing 2 things on board as well while we are capturing the stills and video. The first is one person's calling out observations when they're looking at the screen, which is a live feed video. And then another person who has the more boring job, I guess, gets to log the observations that's being called out using a text logging software. And this logging software that we use is called the Ocean Floor Observation Protocol, which we call OFOP in short. And we've also been using this for almost 20 years. And it was developed by a scientist called Jens Greinert from GEOMA from Germany. And the reason why we've been using it for so long is because it's really quick and easy to set up. And at the end of a transect, you can just easily provide a summary of the observations. So these observation labels, which are mostly substrate, fauna, and flora, they're stored in a reference list in an Excel file. And so in the left-hand column, you've got these unique ID numbers. And so from each voyage, we select a subset of labels from this reference list. And then we format them into a text file for OFOP to use. And so the numeric values on the right-hand side, that kind of determines the label position in OFOP. So for example, labels that are numbered 100 to 199 will appear in the first column, 200 to 209 in the second, and then so on. And then this numbering system controls how the labels are ordered and displayed in the software. So that's just an example of what the buttons look like. And so they're kind of like clickable buttons that you can press on, and then that creates the observation in the text file. And so the result is a text log that records the timestamp and location, and that's being transmitted in real time by ultra-short baseline transponder system, and along with the observation and the ID numbers. And each record represents one individual observation. So for example, you've got 4 records of Astropactinidae sea stars here, corresponding to what's visible in the video frame. So this whole process is really well thought out, and the workflow is pretty smooth. But one of the things that we really have challenges with is how we manage this data. So we are finding that we are collecting these videos and images at an increasing scale, and this is becoming a growing challenge. So as you can see, we've got almost 8,000 hours of video footage that has been collected since 2006. 96% come from New Zealand waters, and then 3% come from the Ross Sea. That's equivalent to 208 hours of footage, but that's also equivalent to about 208 kilometers of video. And that's from 6 cruises between 2008 and 2025. And of all the Ross Sea footage, 80% of that has been analyzed for observations from OFOP. So next we have still images. We have approximately 620,000 images. That's just a rough count. There's probably more. 90% are from New Zealand, and then 8% of them are from the Ross Sea. And from the Ross Sea, we have 51,000 images. And even though it's, like 8%, it's still a very substantial number. All right, so I'm going to be airing a bit of my dirty laundry here. So the imagery and observation data, we don't have a database. Everything is just stored as individual files in the local network drive. So everything's just in a flat file structure. And in fact, some of these files just exist only in project drives and personal drives. So being able to extract these observation files can be really frustrating and challenging. So really what we need is a data platform that can centralize all this imagery and observation data. So today I'm going to be talking about 3 parts of a proof of concept platform that we've been building. So the first one is cloud services that gives us the storage power to manage large volumes of data, a database that keeps the data organized and easy to access. And then finally, I'll talk about machine learning tools that we've built that can help assist automating tasks to analyze this imagery and seafloor data. So we'll start with cloud services. So we need cloud services to manage imagery data and workflows efficiently. So here I've got just an example of a schema that we've built. So we've got raw data that goes into 2 cloud services first, which is AWS or Amazon Web Services, and then MongoDB Atlas Database Cloud. And then we can use software as a service tools or SaaS to then extract and analyze data directly in the cloud for different applications. So here, serverless architectures efficiently process data. So the key part in this serverless cloud architecture is called a Lambda function that was developed by Amazon. And so, for example, when new data is uploaded to AWS, the Lambda function automatically triggers and then extracts this observation data, and it passes them through a processing pipeline. And then the results from these OFOP observation files are then stored into MongoDB Atlas, ready for querying and retrieval. So the benefit of this is how cost-effective it is. So first, it's event-driven. So you only need to use computing resources when needed. And it also scales automatically as data volumes grow. And it also saves time and costs by not running constantly with such as traditional servers. So we currently have over 100 AWS resources and services running at Earth Sciences, but the total monthly amount is apparently $3 USD, and that's not counting storage. So integration with SaaS streamlines seafloor image annotation. So our image data is currently stored in S3 buckets, which provides a simple and scalable cloud storage. And apart from OFOP annotation, we also use another annotation tool called Biggle 2.0. And it's a web service for annotating marine imagery specifically. And it allows you to connect securely to S3 buckets or other type of cloud-based storage using access credentials. And this gives image analysts a direct way to access the data. They can create annotations without needing to manually download or transfer files. So the next thing is our database, which is pretty cool because we haven't had a database for 20 years. And you'll see why. So the problem is that our OFOP observation data isn't suited to a traditional relational database. So we tried using it in the past, but this is the problem here. So every piece of data needs a defined structure in the relational database, right? It needs to match up exactly with a primary key, so that you can see on the left-hand side. So in our data set, the labels don't always match the reference IDs. So for example, on the left, you've got ID 816 that's listed as Lepidian, which is a cod of some type. And then on the right-hand side, you've got this OFOP text file that has the same number, but it's called heart urchins. And these inconsistencies, which are really prevalent across the text files, they make this relational database hard to use, and it requires a large amount of data grooming. And I mean, trying to groom 20 years of data is exceptionally challenging, and that's why we haven't had a database until now. So to resolve this issue, we use MongoDB, which is a flexible non-relational database that handles semi-structured data. It's cloud-based, it's NoSQL, so it doesn't need a predefined schema. And so here it stores information in a JSON-like format, and it allows each entry to have a different structure. And it works really well for our OFOP text data here, because our records, as I said previously, it can vary in content and format over the years. And also it's got this aggregation pipeline that sorts these text files into different data collections that you can see on the right. And it also has various options for viewing this data. So you don't have to just look at it in the JSON format. So here I've just got it here as a table format where you can browse records, filter, or sort the data as needed. And then not only that, it supports plain language search queries. So if you're a marine ecologist like me that does not understand SQL syntax or other various syntaxes, this is great. So you can put in there, like, search this cruise for this station, and then it automatically converts into this MongoDB syntax. And so, yeah, it allows users to search the database without having to understand these type of typical queries. All right, so the machine learning side of things. So once we have a data platform that makes data really easy to work with, this allows us to find kind of interesting ways to work and explore the data. So the three parts that we are currently working on with this platform is that we can build these different machine learning interfaces to help explore the data. We're also using SageMaker to run machine learning pipelines for object detection models, and then setting up this human-in-the-loop and continuous learning workflow to keep improving these models' performances. We're currently in the process of building the machine learning pipeline and then figuring out how to also optimize this workflow. Okay, so we're really excited about this tool. It's using a chatbot that talks to the observation data in MongoDB. So the chatbot runs on Claude 3.5 Sonnet, which is a type of large language model. And then it connects to our MongoDB database, which is using a process called Model Context Protocol, or MCP. So I hope I get this right. I think so. The Model Context Protocol is an open standard that allows a large language model to securely connect with an external data source. It could be a database, it could be APIs, it could be your local files. And here the MCP allows the Claude chatbot to query and retrieve these observation data from MongoDB in real time. So for example, your user could say, please show me a summary of some observations from a cruise. And so the chatbot uses the MCP to So it allows the chatbot to query and retrieve these observation data from MongoDB by pulling relevant observation records and running the aggregation pipelines to compile the summaries. And then it returns a clean summary to the user. And this setup keeps this chatbot context aware and also focused on just the relevant data, so no redundant information. And then this is what's returned from the chatbot. So during testing, users often ask for extra outputs, such as Excel summary tables or mapped visualizations. We haven't added these features yet, but it's something that we will think about doing on our to-do list. And what's really cool about this is that the chatbot can recognize and group taxonomic data. So for example, here it's grouped these bryozoans together. So it shows that the chatbot isn't just retrieving data, it's also interpreting and organizing this data in meaningful ways. So how has this been made possible? So the reference list that I showed you previously, so it's been converted into a network graph using the Neo4j software. And it allows you to visualize and explore these connections between taxa. And this has been linked with the World Register of Marine Species API that allows us to connect these taxonomic levels. So on the left, the arrows are quite hard to see, but it shows you a complete taxonomic graph. And then on the right, it's just zoomed in. It's just zoomed in to show you the structure. So the purple nodes that you see are the species, and then the brown nodes is the genus. So you can see the arrows are kind of connecting to the genus here. So the user can ask about taxonomic details now that it's got this knowledge graph that it can take advantage of. So for example, a user can ask, okay, give me a taxonomic information about the solitary cup coral called flabellum. And the chatbot retains this conversational context from earlier prompts, such as if you were asking about the Ross Sea region. And then because of this, it can use this context to fetch and return the taxonomic hierarchy for that coral. But of course, like any large language model systems, it can make mistakes. So it may list species, for example, that don't actually occur in Antarctic waters, so it actually hallucinates as well. So some of the ways that we're thinking of mitigating these problems is to obviously have a disclaimer added saying that the chatbot's not going to be 100% accurate. We're going to keep stress testing and also sort of running automatic checks against trusted sources like worms to flag incorrect classifications. We'll also have to implement guardrails, and also I think we'll probably also try and add these requested features from the users that have been testing this, such as exporting these Excel files and maps so that they can verify and visualize these results. So before I dive into the SageMaker object detection pipeline, I think, why are we doing this? And as an image analyst, I can sort of truthfully say that, manually annotating these images, it's really tedious. It can take hundreds of hours to process, and that's just from images or video from a single cruise. And, that's mentally and physically exhausting as well. So the idea is that we use object detection to reduce the workload and assist the analysts, but then still keep this as, just keep them in the loop as well. So like the previous pipeline earlier, like Lambda function is triggered by events and runs these machine learning pipelines. So here the workflow starts with a pre-trained object detection model called, and that scans images and identifies the objects that it's trained with. The model then tries to detect objects and match them with observation labels stored in MongoDB, which we call annotation matching. And then the results are then sent to the BIGL web annotation tool, where experts can then review and validate them. So here we've just talked about cloud services managing imagery data and workflows. So I'll just draw attention to a specific part of the workflow, which is a human in the loop and active learning loop. The expert feeds back into the model, learning from corrections, and then improving performance over time. And then the model reduces errors in future predictions. So the SageMaker annotation pipeline, that's what we start with. And then the results are stored in an AWS S3 bucket. And the results are then posted to BIGL using an API. And this creates a project folder and then posts these annotations from this model. So the bounding boxes and the labels are all derived from the OFOP observation data. And then here, experts such as taxonomists, image analysts, collaborators are then invited to review a project on BIGL, and then they can make these corrections directly in the interface. So for example, here, like the models just missed a few objects, and that can be added by the user. And then once the corrections are done, it triggers another pipeline that retrains the model, and then the whole process repeats again, and this is the continuous learning loop. All right, so that's it. So looking ahead, we've got a few key questions that we're exploring. So, how do we increase the accuracy of machine learning models? And that's the work in progress. And then can we improve the understanding of the large language models of the raw sea data? And then how do we improve the interoperability between our data and other platforms so that we can work together more seamlessly? Can we integrate these other platforms to link ancillary data like environmental measurements or sensor data? And then for the wider polar community, how do we make this data platform accessible to researchers? So that's it. If you have any questions, yeah, happy to take them. Thank you.
Is that on? Yes? Okay. Thanks, Caroline, for a fascinating talk. That's an enormous amount of work that's gone into that project. We probably have time just for one quick question. Nope? Yeah.
Hey, yeah, I'm really impressed by the work for the annotation and all the stuff. I'm wondering, how does it work? So when you're coming from the images, you have the assignment of all the informations with latitude and longitude. So it's geo-reference in time and also geo-reference in time. But I'm wondering how it works also with all persistence identifier. How do you build then data sets out of it? So also to referencing back when you do the annotation, either with the using the large language model or using Beagle and so on. So because that's also always a challenge to track back the precise image you have taken for annotating, and along this pipeline. So have you solved this in a good manner, or
no? It's really tricky. So it also depends on the type of model that you're trying to use to match the OFOP labels, the observation labels with the images. So we've tried using like a supervised detection model that's pre-trained called RFDTR, and it kind of guesses what the objects look like. It doesn't know. So it just kind of looks for an object because it's also learned, it's learned labels, during training. So it guesses where the labels are going to be placed in your image. So that's why it's really important to have the people in the loop, because it's not going to be 100%, and we all know that. And I think object detection, particularly for marine imagery, is really challenging for various reasons. So it will get better. It's just to start, you're just going to have really, really horrible results, and you just got to. So that's why you've got to have this human in the loop, right? This continuous learning. So it will continuously improve over time. But it's still not going to be 100%. You'll always need some expert to sort of partake and review the data that the model sort of outputs.
Yeah, thank you.